Okay, so let's have a bit of a return to our example with the websites. So we have website 1 or website A. And website B. And this has a kind of the mean return or a mean customer spend or whatever of mu1. And we have the mean customer spend for website B. So what we want to do is we want to work out, whether website A or whether website B has a bigger spend. And we're going to do this with hypothesis testing. So we're actually going to go through the two one-tail tests. And here, our null hypothesis is going to be mu1 minus mu2 is going to be equal to 0. And that's just kind of, they're both the same. Both the means are the same. Or we could actually do mu1 minus mu2 is greater than 0. Now just think about it, and this kind of confuses people sometimes. What exactly does that mean? Well, we just put the mu2 to the other side, and that just means that mu1 is greater than mu2. So we're saying, hey, website 1 has greater revenue than website 2. Okay, so we can then do the one tail lower. And here, the null hypothesis is always the same. We're just basically seeing if these guys are equal. But now we're going to say mu1 minus mu2 is going to be less than 0. Now, what does that mean? Well, we put the mu2 to the other side, website B, and we're going to say that mu1 is less than mu2. So we're trying to show that mu1 is less than mu2. So again, it really is exactly the same as before. The test is the same as before. The only difference is that our kind of null hypothesis is that these two groups are equal. We can actually set an equivalent of mu0, which we call d0, which is like, website 1 is 5 greater than website 2. Or website 1 is 3 less than website 2. But that makes things incredibly complicated and is rarely used. So let's look at the two-tail. And here we have mu1 minus mu2 equals 0. And my HA is mu1 minus mu2 is not equal to 0, i.e. the two websites are different. So again, we're looking in either direction. Now the test statistic so again, it's like we have our sampling distribution, as we did before, which is centered at, in this case, for H0, we're assuming that they're 0. So this is basically mu1 minus mu2 is 0. And basically, we have a sample, which is the difference between two means, somewhere here. So this sampling distribution basically is made up a lot of the differences between the two means, etc., etc. And by the central theorem, that's the limit theorem, that's going to be normal. And again, the standard error, as with the confidence interval example, is this kind of combination of the two variances. So it's going to be sigma 1 squared over n1 plus sigma 2 squared all over n2. So again, if we want to do these tests, we want to turn this little point here, our x1 bar 1 minus x bar 2, into a z. That's all we're doing. We want kind of a z. We want this centered at 0, and we have a standard error of 1. So we have our x bar 1 minus x bar 2. And we're going to subtract the mean from this distribution, but whoa, it's going to be 0. So it's going to be 0, which we don't have to worry about. And then we divide by the standard error. And that is my z statistic. And again, depending on the test, it's exactly the same as before. So what I'll say, one-tailed upper. We're going to reject H0 if z is greater than z alpha, and one-tailed lower. Reject H0 if z is less than z alpha, and the two-tailed so once we have the z statistic, our test is no different than before. Reject H0 if the absolute value of z is less than or equal to, is greater than z alpha over 2. So again, all we're doing is we're kind of exactly as we did with the one sample case. Let's just kind of do the final example, a two-tailed. And I'm making this far too small, so that's z alpha over 2, z alpha over 2. I'm going to move my thing down a little bit. So we have a z value somewhere in here. And, you know, we kind of, as we get bigger and bigger and bigger and bigger until we reject, we get smaller and smaller and smaller and smaller until we reject. So again, very small differences we don't reject, large differences in either direction we do reject for a two-tailed test. And for all these tests, exactly the same as before, I kind of showed you the logic. We also can reject if p is less than or equal to alpha. Now, the t-test is actually a little bit more complicated for the two-sample test, which is why I'm not going to spend a lot of time on it in terms of the mathematics. You can kind of look that up from a stats book if you really want. So if we have a t-test, we have a student's t-test. And this is only if the groups have equal variances. And again, I'm not going to do a lot of the math of this. We're just going to kind of do it in R. And here, so it's just a stat. I'm not going to do the hypotheses because they're exactly the same as the z-test. But t is x bar 1 minus x bar 2 all over the square root of, this should look familiar from the confidence intervals, sp squared 1 over m1 plus 1 over n2. So it's essentially the hypothesis test version of the small sample confidence interval we did before. But there's also another guy, and this actually has degrees of freedom of n1 plus n2 minus 2. So when we kind of do the test statistic, we have to calculate these kind of degrees of freedom. Now, we also have the Welch's t-test. And I'm not going to give you the math for this because it gets a bit complicated. It's got this like insane degrees of freedom calculation. And this is that the groups have unequal variances. And you can actually kind of just look this up. I think I might have put it in the notes. But how do we check if they have equal or unequal variances? Well, we use something called Levene's test, which is explained in the notes. Let's just kind of go back to the notes. It's getting, oh, it's because I've got my pen rested somewhere. You see here, this actually from the notes actually just gives you what I've just said. There's a z-test, then it has the student's t-test, and then it has the Welsh's t-test. And I always say to my students when I was teaching business stats, I'm not that evil. I don't make you do the Welsh's t-test, because that V there, that's actually your degrees of freedom calculation for the Welsh's t-test. So let's kind of just quickly run these in R. So first we're going to do the manual z-test. And again, I'm not going to make you do these. This is just writing out the equation that we had before. So we set our alpha. The data set, the A/B testing is as before. It's just literally a column with spends on website A and a column on spends of website B. We calculate the standard error, which is the square root of the variances of group 1 over N1 plus the variances of group 2 over N2, and that they're both the same for this example. And we have the standard error. And we have the difference between the means, x bar 1 minus x bar 2. And my z-score is just the difference. And we're going to do a two-tailed test. We pretty much always do two-tailed tests in this class. We're going to reject if the absolute value of z is greater than z alpha over 2. As I said, in R we go from left to right, so it's like rather than going to the right of z alpha over 2, it's 1 minus z alpha over 2. And then the p-value, again, we're just basically taking the smaller value. If I'm to the right, if my z is greater than 0, I go to the right. If my z is less than 0, I go to the left. And because it's two-tailed, I multiply it by 2. And then I paste in the results of the test. Okay. And you can see here that we have a low z-score. And the critical value is 1.96. So we failed to reject, and we have this whopping large p-value. So let's have a quick look at, and just make sure I did this correctly. I'm just going to do it all from the beginning. Oh, so I obviously didn't calculate my z correctly. And maybe I just forgot to update my n, which I always do. But anyway, we have a large negative z, which is big. The absolute value is bigger than my critical value, so I reject. And my p-value is very small. It's definitely less than any standard alpha, so I reject. Now let's do the same with the t-test. So if you want to run a student's t-test, then we do group 1, group 2, and we have var.equal equals 2. True. So very simple. Group 1, group 2, the first column, the second column, and we select equal variances. And that's basically the t-test. So we get the t-value minus 2.7743, almost identical to the z-value. Degrees of freedom, both my n's are 500, so 500 plus 500 minus 2 is 998. And we got this very small p-value. So we can say here this is negative, so we have a lot of evidence that mu1 minus mu2 is less than 0. So there's a greater spend for website 2 than website 1. And again, this test also gives you the confidence intervals, and we have the confidence interval is less, doesn't go through 0. So again, that's more evidence that we're actually kind of less than 0. If you have the same kind of standard error, rejecting a two-tailed test is equivalent to saying that the equivalent confidence interval doesn't go through 0. And then we do the Welsh's t-test. And we get pretty much the same result. Our p-value is very slightly different, very slightly more. And how do we actually decide which of these to use? Well, in the library of car, so we load the car library. There's something called Levene's test. And what Levene's test does is the null hypothesis is the variances of equal, and the alternative hypothesis is that the variances are not equal. And Levene's test is trying to load. Okay, sorry about that. Car required like a few minutes to actually install. Okay, so now we run the Levene's test. So what we have to do is, interestingly, Levene's test takes in a slightly different format. We basically have to have the vector of all of our results. So we have to put the first 500 in group 1 and the 500 in group 2. And then we have to actually say which group they are. So we actually have to have group 1 and group 2. And we actually just kind of basically, as factor means we're passing a factor, and we're just having an indicator what's group 1 and what's group 2. We run the Levene's test. And here we reject the null hypothesis. The null hypothesis is the variances are equal. The alternative is the variance is not equal. So if we reject the null hypothesis, then we should use the Welch's test. So in most instances, there's not a great deal of difference. So here we say, okay, p-value is 0.005642, which is less than whatever our standard alpha is. We can reject the null hypothesis. Okay, guys, so thanks for sticking with this. I realize that it's pretty dry, but this is kind of one of the foundations or building blocks that we're going to need as we move forward into kind of more interesting, more advanced techniques. And hopefully should have linked a little bit to what you did with business stats.